Hello again, my dear students. Now, this is part number two, with lecture number two under the title Introduction to Communication, Introduction to Analog Communication or Analog Modulation. Now, uh, if you remember, by the end of part number one, we have concluded that in order to transfer from a passband signal located around the zero to a in order to transfer from a baseband signal located around the zero frequency to a passband signal around any arbitrary frequency FC, then you have to do what's called modulation. And we have proved that this modulation process is simply a some sort of a multiplication process in the time domain or a convolution process in the frequency domain. And we mention this fundamental example. This is actually the start of our part number two. What if we are going to modulate a very simple monotonic sinusoidal signal with a frequency of f with a carrier with a frequency of c? So here the input signal is just a tune, a monotone with a frequency of m, and this is a carrier frequency as we proved in our first part that it should be a sinusoidal. Then we are going to do this process. Again, my dear student, whenever you are going to solve such a problem, you can solve it either in the time domain or the frequency domain. If you remember in chapter number one, when we deal with a signal inputted to a low-pass filter, we solve it in the frequency domain. And I told you that you can make it in the time domain with the same manner. Now, we are going to solve it in both time domain and frequency domain and prove that we will have the same solution by the end of the day. So let's start solving this problem step by step. Okay, now I think you can see my whiteboard or white paper actually, and then let's start solving this problem. Oh yeah, this problem. Okay, so the problem is very easy. As we say that this is just a multiplication in the time domain, so we have this multiplier. By the way, electronically we call it mixer. And here we have a signal AM cosine 2 pi FMT. And here we have the signal AC cosine, of course they can be sine or cosine 2 pi FCT. And we are now seeking for an output, what we call the S of t or the modulated signal. So simply, S of t is the multiplication of AM cosine 2 pi FMT times AC cosine 2 pi FCT. Here you have just to return back to your high school mathematics or high school trigonometrics to remember this relation. Cosine A times cosine B. Whenever you are multiplying two sinusoidal signals, here specifically they are cosine, whenever you are multiplying two cosine signals together, what is the output is? Okay, so by returning back to our basic trigonometrical functions operator, you will find that, okay, so cosine A times B is simply equals to half cosine A plus B plus cosine A minus B. This is simply the mathematical expansion of this cosine. So by doing this such a very simple example, so S of t will be equals to AM times AC. So this is just multiplying the two amplitudes. And then this will be over 2 due to this half. And then you have the summation of these cosine arguments. So cosine 2 pi FC plus FM plus the cosine of the summation or the subtraction, cosine 2 pi FC minus M. This is very simple what happened. So let's now try to make it so now S of t equals to AC AM cosine 2 pi FC plus FM. Here is over 2 and here there is a bracket plus cosine 2 pi FC minus FM and then close it. Okay, this is a very important time domain signal. Maybe in the next lecture, in the amplitude modulation lecture, I will tell you, or we will work together in order to plot this very interesting function in the time domain. But for this exercise, I will just ask you to plot it in the frequency domain. Should be easy because due to the linearity property of the Fourier transform, you can deal with each term of this sinusoidal signal separately. So you have two sinusoidal signals. The first one with a frequency called FC minus FM, FC plus FM. So yeah, what we are going to do is, okay, this is the frequency domain. This is the S of t. Right now this is the S of F, and now this is F. I would like to plot. So first I have a sinusoidal cosine, then I have the frequency is called FC minus FM, FC plus FM. So this is the first one, FC plus FM, and it has an amplitude AC AM over 2, and then this is the other component, which is simply minus FC plus FM with the same amplitude AC AM over 2. Now let's do the other sinusoidal. It's another cosine with a frequency FC minus FM. I'm sorry, I forgot to mention here there is a T and here there is a T. I'm sorry. This is the time limit. So now for the other signal, it has a frequency called FC minus FM. And here another frequency FC minus FM. And here is the two components, and then AC AM over 2, and here is AC AM over 2. So this is simply the modulated signal in the frequency domain. So this is the time domain signal, and this is the frequency domain signal. But now, okay, let's do it from the other side. This is the time domain side, and then we make an inverse, sorry, a Fourier transform. So what if I do the following? Okay, you told me that the input signal is a sinusoidal signal in the time domain. So M of t, the input is AM sine 2 pi FMT. So if I would like to make the frequency transform for this signal, you will say this is very easy. It is somehow this is the zero frequency and this is the F here. So we have something like FM here and the FM here. So you can see that I make it very close to the zero frequency because I am assuming that this is a baseband signal. That's why I make this FM is very smooth. And this is very, by the way, very important that logically speaking, in this example, we have to say that FC is much greater than FM because this is a baseband and this is a passband. So this makes sense with what we have already studied in the lecture. So this is our baseband signal. So where the carrier is C of t equals AC cosine 2 pi FCT. So when I would like to make a shift, then I will make something like that. This is FC and this is negative FC. Now, what if I would like to make this process in the frequency domain? So this now I will make what's called a convolution. And if you remember, what I told you about the convolution is simply is that you shift the signal to the place at which the delta is. So this is your signal, this is your frame. Now this frame is centered around 0, and due to the convolution with delta, this signal will be shifted at this one. So now you will take this portion and shift it here. So what you will get is as follows. Now this is this signal shifted here, so you will have this signal. Now the center is not 0, the center is FC. So this is FC plus Fn, and this is FC minus Fn. And typically, a symmetric way, you will have these two dots. Okay, so this is a very, very simple manner in order to make such a convolution process in frequency. Of course, herein this is somehow easy because you have just a signal in a time domain which is sinusoidal, so you can make it easily in time and frequency. But later on, you will find that it's somehow easy to make it in one perspective rather than the other. So you will choose to make it, for example, in the frequency domain. And again, this is another solution or another answer for the question why we are using frequency domain, because here why it is easy in frequency domain. You just take a copy of M of t and then shift these M of t on the right hand side and on the left hand side. That's all. So you get this modulation. So as you can see, here we make it in two different manners. In the first slide, we make it purely in the time domain, and then we make a Fourier transform. Herein, we make it purely in the frequency domain from scratch. So you can make it by both sides, and by the end of the day, you will get the same answer, or you will get the same conclusion. So this is the first example here in this part. Let's now return back to our slides, please. Okay, so again, my laser point. So now we have reached the output of such a signal. We know now how the multiplication process reflects on the time and the frequency domain. We know that the multiplication process is simply, sorry, the modulation process is simply a multiplication process. But here, life is easy because you have a very easy, very simple, I call it the most simple input message signal, just a tone. But relatively speaking, or generally speaking, this M of t can be any and every signal. It is just a message, maybe a voice, maybe a video, everything. So, what if this input signal is just M of t? Some signal in the time domain which is unknown, any M of t signal. What will happen? So let's now repeat the example. Now we have generally any M of t signal. So your input is M of t. Again, you have the same mixer, the multiplier, and here we have this AC cosine 2 pi fct. And now this is the output, the S of t. Okay, so please write a general form for S of t. Very easy. S of t is equals to M of t AC cosine 2 pi fct. It's very easy. But where's the observation? Please consider this. Now, in this output signal, it is typically a carrier. If you make a comparison between this carrier signal, the C of t, and this output modulated signal, which is S of t, if I told you, please make a comparison between these two signals, yeah, let's now see. So what about the cosine term? Exactly the same. Cosine 2 pi fct, cosine 2 pi fct, no change. But the only change is here. You have now a
time dependent amplitude. The amplitude of this sinusoidal signal is now a time dependent. It depends on time. Actually, not generally in time. It depends on a specific time called m of t, which is your message. Your amplitude now carries the message. That's why we call it carrier. So you carry your message in the amplitude. And herein, we will call it amplitude modulation. Why it's called an amplitude modulation? Because simply the message content is hidden in your carrier, in the amplitude of your carrier. So, does modulation means amplitude modulation? Does amplitude modulation covers every and all modulation techniques? The answer is no. Let's go back to the slides. So, okay, so here is the example. So this is a general message. Now we get this output. We already see it. We already see. I believe I did a wrong share. I'm sorry for that. Yes, I think this is now good. Okay, so very perfect. So okay, now it's true. Okay, so this is the output. So now let's turn. This is our carrier. As I mentioned, we hide our message now inside the carrier. But let's start and think. Is it the only way to hide the message inside the carrier? Is there any other way where you can hide your message in, or in another form? Does the carrier include any other parameter rather than the amplitude? Let's see. Of course. Okay, of course the carrier include the amplitude as a parameter. This is of course. However, cosine 2 pi, okay, but we have another parameter, the frequency. And actually we have a third parameter, which is the phase. So generally, the carrier include three main parameters that are capable to be function of time. We can make the amplitude function of time, or mainly function in the message. We can make the frequency function in the message. We can make the phase function in the message. So, if we make the frequency function in the message, we will call it, sorry, if we make the amplitude function in the message, we will call it amplitude modulation. Here, your message is hidden in the amplitude of the carrier. If we make the message hidden in the frequency, so the frequency will be time dependent. Do you believe it? The frequency will be a time dependent function. Then we will call it a frequency modulation. And if we make the message hidden in the phase, we will call it a phase modulation. So generally speaking, whenever you have a carrier, you have three variable parameters that are capable to include your message, either the amplitude, or the frequency, or the phase. These are the three main variables that are capable to hide, to carry your baby, your message, I mean, to your receiver. This is simple like that. So now, I'm sorry. Okay, now this is about an analog communication. Let me for a while ask you why we call this an analog communication. Do you remember? Okay, let me return back. Okay, so do you remember this system? Why it's an analog communication? Do we call it analog because the carry is an analog signal? Because it's a sinusoid is an analog signal, of course. Simply, the answer is no. We call it analog because the message is analog signal. So this, I'm sorry, yes, this is an analog signal. And this is an analog signal. By the way, I believe that you already know the difference between analog and digital, or a continuous and discrete. So analog signal is a signal which have a values, a variable values on the y-axis. As you can see here, the y-axis, which is the amplitude axis, can accept any value, like this one, any value. So what about digital signals? Or what about digital modulation, which is maybe the 50% other part of our course? It's very simple. The same block, the same procedure will typically be applied, but the only difference is here. Your input signal will be converted to be digital. Of course, you are a computer engineer. You are a genius with digital, so you know a lot about digital electronics and digital signals. So now, what you are going simply to do is to add this important proc, analog to digital converter, before your modulation proc, in order to keep your message from an analog to digital. Because physically, any converted physical signal will be directly converted into an analog signal. If you convert my current voice, it will be an analog, as you already see in our MATLAB task, which is one of our bonuses, if you remember. When I told you, just go to the MATLAB, pick up your mic, record your voice, convert it and plot it in the time domain, do Fourier transform, transfer it in the frequency domain. That's all. So the output is an analog signal, but I need to make it digital. I need to make a digital DV. So I mean a digital channels like what we already have now in our satellite, or maybe even on our local TV. So to make such a digital DV, you need to make this analog to digital conversion here. So you need this step. And of course, you need the reverse step by the receiver, which is digital to analog, to make it again to its original image. So simply, the main difference between the analog communication and digital communication is related to the message, not to the process. The carrier here is still analog. You will use the same sinusoidal analog signal as a carrier. However, your message is a digital signal. This is the main difference. As I told you, our current lecture is somehow a short lecture. So maybe this is something good to take a while before going to the analog modulation, which will be the topic for the next week. However, I believe that this lecture includes a lot of very, very, very important concepts. So I hope that you get what I'm expecting you to receive. It's not only mathematics and multiplications, it's more toward concepts. Thank you very much for your concentration. Please accept my invitation to the next chapter, which is the amplitude modulation chapter, by next week, inshallah. Thank you very much.